Okay, welcome to lecture 23. We're on unit 3 of the course, the Laplace transform. And so today we're going to look at some properties of the Laplace transform, the first translation theorem and the Laplace transform of derivatives. So this is going to be where we start to encounter using Laplace transforms to solve ODEs, which is of course the purpose of this class. And then secondly, well, if we take the Laplace transform of a function, we better be sure that we can go the other way as well. Okay, so we're going to learn about something called the inverse Laplace transform. But we're going to jump into something called the first translation theorem. So given that some function f of t that does have a Laplace transform, well, we know that we can write this as the Laplace transform of f of t is equal to this capital F of s for some value of s. It has to be greater than some number c. The Laplace transform of this function f of t multiplied by this exponential of e to the at. So now we're not taking the Laplace transform of f of t, we're taking the Laplace transform of the product f of t times this exponential. So that is given as the Laplace transform of e to the at times f of t is equal to this function f of s minus a. Okay, so previously the Laplace transform of f was given by f of s. Okay, but now we've got, if we're taking the Laplace transform of the function multiplied by this exponential, we've got the s minus a. Okay, the a comes from the constant in the exponential. Okay, and again, this is true for s greater than some number c plus a. So s had to be greater than c for the Laplace transform of this function f of t. But now, because we multiplied it by the exponential as well, s has to be greater than c plus a. Okay, and this is known as the first translation theorem, sometimes referred to as the first shift theorem, but I'll try to stick to the first translation theorem. Well, and maybe the word first gives away that there's going to be a second translation theorem later in the class, well, later in the course. Okay, and the proof of the proof of this first translation theorem is found using the definition of the Laplace transform, which involves lots of integration by parts. So you can look in the textbook if you're interested in that, but I'm not going to go through it in class because it's quite a lot of work. So what I'd really like to do actually is just show you an example of how this works with real functions. Okay, so we're going to take the function, the sine of b of t, so b is some constant here. If I take the Laplace transform of sine of b of t, which is equal to my f of s, so my transform function f of s, well, from the previous class we recall that this was equal to b over s squared plus b squared for s greater than 0. Okay, so this is just revision from the last class. Okay, but now instead, if I don't want to take the Laplace transform of sine of b of t, what if I want to take the Laplace transform of sine of b of t multiplied by this exponential of at? Okay, well, by the first translation theorem, I know that this is equal to the function f evaluated at s minus a. Okay, and I know the function f of s is b over s squared plus b squared. So all I have to do is say wherever I see s in this function, I'm going to replace it with s minus a. Okay, so here I have an s squared, in fact, here in red in the original function f of s. So now I see an s, so I'm going to replace it with an s minus a. So s minus a squared. Everything else is the same. We've got a b on the numerator and we've got a plus b squared on the denominator. So I hope you can see how that works. Basically, if we multiply a function by e to the at, wherever you see an s, you subtract an a. So s minus a squared. S squared becomes s minus a squared. And again, this is valid, the Laplace transform of this new combined function is valid for s greater than a, because it's 0 plus a is a. Okay, so this first translation theorem is going to be really useful when we want to study functions that are multiplied by exponentials. Okay, or let's say when we want to take the Laplace transform of functions that are multiplied by exponentials. Okay, we can also take the Laplace transform of derivatives. Okay, so assuming that this function f of t is piecewise continuous on 0 to infinity and it has at least two derivatives. So what? Well, in fact, we can take the Laplace transform of higher order derivatives as well, but in this class we'll just focus on first and second order derivatives. So assuming that these exist and are piecewise continuous on this interval 0 to infinity, with exponential order c for some s greater than c, then we can actually write down the Laplace transform of the derivative of f of t is equal to s times f of s. So remember, f of s here is the Laplace transform of f of t. So s times f of s minus the original function f evaluated at t equals 0. Okay. So this is actually kind of interesting because this minus f of 0 thing here, this is kind of like an initial condition, right? It's when t equals 0, what does f equal? Well, it equals this thing here. Okay, and similarly we can do the same thing for the second derivative. So the Laplace transform of the second derivative of f is equal to s squared times the Laplace transform of the function f of t, so f of s, minus s times this initial condition when t equals 0, the original function equals f of 0. Take away, it's kind of like this second initial condition, right? What is the derivative of this original function f of t when t equals 0? So using the Laplace transform, we can actually get rid of differentiation altogether. Okay, we basically replace differentiation with respect to t with multiplication with respect to s. So here we had a first derivative, so we had a 1s times the Laplace transform of the function f of t. Here we had a second derivative, so we had an s squared, so 2s times s, 2 times the Laplace transform of f of t. So we basically turn a differential equation into an algebraic equation. Okay, so derivatives here, we've got a differential equation. But if we take the Laplace transform, we turn it into an algebraic equation with respect to s. So it's just s and s squared. But in fact, it's even better than that, right? Because we're actually not even turning a differential equation into an algebraic equation. We're actually turning an initial value problem into an algebraic equation. Because this thing f of 0 and this thing f prime of 0, these are initial conditions. Okay, so this is going to be really useful to solve, I say here ODEs, but in fact I mean initial value problems. Okay, so before we look at an example of that, I just want to prove this first relationship here to you. So if I want to look at the Laplace transform of the derivative of f, then by definition this is equal to the integral from 0 to infinity, or of course you can write this as the other way, limit of n goes to infinity of 0 to n. But okay, we'll just look at this for now. The integral between 0 and infinity of e to the minus st multiplied by the function we're taking the Laplace transform of, which of course in this case is f prime, the derivative of f. Okay, and we can solve this by integration by parts, right? Because we got one function of f multiplied by another function, one function of t multiplied by another function of t. Okay, you might like to try that, but basically what we get is we get e to the minus st times the integral of f prime, so we get f here. So e to the minus st times f, evaluated at infinity and 0, plus s times the integral from 0 to infinity, e to the minus st times f of t dt. This second term here, this integral term here, this is the definition of the Laplace transform of the function f of t. So I can actually write that as s times the Laplace transform of f of t. Okay, so well, maybe I'll do that. S times the Laplace transform of f of t. Okay, That is exactly the definition of the Laplace transform. This integral is the definition of the Laplace transform of the function f of t. Well, the first term here, I should look at that. Well, if I substitute in infinity for t here, well, because s is greater than 0, this term is going to 0, okay? If I substitute in t is 0 in here, this term becomes 1, and I just get f of 0. Okay. So therefore, the Laplace transform of f prime of t is just equal to negative the original function f evaluated at 0 plus s times the Laplace transform of that function f of t, which can be written like so. Okay, so instead of writing this fancy L, the Laplace transform of f of t, I can just write that as capital F of s. Okay, so it's a fairly standard proof, fairly straightforward proof. But let's look now at an example. So we're going to look at a couple of examples, but firstly we're going to look at the Laplace transform of sine of b of t. We know that is equal to b of s squared plus b squared. Okay, and we're asked to find the Laplace transform, given that we know this, we're asked to find the Laplace transform of cosine of b of t. Okay, well, how can we do that? Well, we know that sine and cosine are related by differentiation. So we know the derivative of sine of b of t is equal to b times cosine of b of t, right? So we can find the Laplace transform of cosine of b of t by actually calculating the Laplace transform of the derivative of sine of b of t, divided by this b because we have a constant b over here. So cosine of b of t is equal to 1 over b times the Laplace transform of the derivative of sine of b of t. Okay, well, according to my property of derivatives, the Laplace transform of the sine of b of t is equal to s times the Laplace transform of the function, so s times the Laplace transform of b of t, minus the function evaluated at 0, so sine of 0. Well, it turns out that sine of 0 is 0, right, so that's easy. So we just simply get 1 over b times s times the Laplace transform of sine of b of t. Okay, so just equating those terms there. Well, sine of 0 again I said is 0. Laplace transform of sine of b of t is this thing b over s squared plus b squared. The whole thing's divided by b, so that b is going to disappear on the numerator. The whole thing is multiplied by s, we're going to get an s on the numerator as well. So just writing that out here, we get the Laplace transform of cosine of b of t is equal to s over s squared plus b squared. So this is actually quite a nice way to calculate the Laplace transform of some new functions, right? So if you know the Laplace transform of function a, you take the derivative of function a, you get a new function, okay? Using this property, we can find the Laplace transform of that new function. More often than not, though, we use these two properties to solve initial value problems, and we'll come to some examples of that. Okay, so just to summarize what we've done so far, well, we've learned a few things. We've learned that the Laplace transform is linear, so these two properties here are just essentially saying that the Laplace transform is linear, a linear operator. We've learned this thing called the first translation theorem. So if we take some function f of t, which we know the integral of, we know the Laplace transform of, and we multiply it by e to the at, the Laplace transform of this product of functions is equal to the Laplace transform f of f of t evaluated at the new point s minus a. We've also learned the Laplace transform of a first derivative and the Laplace transform of a second derivative. You can generalize this to the nth derivative, okay, so you have a lot of terms here, but we're really only going to focus on these first two cases, the first and the second derivative. Okay, but one that I haven't shown you yet is, what if I have a function f of t, and instead of multiplying by an exponential, I multiply by a polynomial here. where n is an integer. So t to the power of n times a function. Well, it turns out that that is just equal to -1 to the power of n multiplied by the nth derivative with respect to the new variable s of the Laplace transform of f of t. So I can write this as -1 to the n dn by ds to the n of f of s. The Laplace transform of a polynomial in t multiplied by f of t results in taking derivatives in the variable s. So I can show you, we'll look at an example of that shortly. And I also have this one from last time that I've kept around because I'm going to want to use that in a minute. So let's look at example. So we want to look at the the Laplace transform of 2 times t squared times the exponential of minus t plus cosine of 4t. So we know that the Laplace transform is linear, so I can write this as, this is equal to 2 times the Laplace transform of t squared times e to the minus t minus the Laplace transform of t plus the Laplace transform of cosine of 4t. Okay, well, these two here, the second term and the third term here, these are pretty easy. The Laplace transform of t is 1 over s to the, well, t to the power of 1, so s to the 1 plus the power 1, so s squared. The Laplace transform of cosine of 4t is s over s squared plus 4 squared, so 16. But what we want to do now is evaluate this term here, because here we have the product, a polynomial t squared times this exponential of minus t. Okay, so what is this term equal to? Well, what I know is the Laplace transform of t squared is equal to 2 factorial over s cubed. Okay, so if the power is 2, the s is to the power of 3. Okay, and I've got this 2 out front here, so I'm multiplying this whole thing by 2 as well. So that is from this property of Laplace transforms on this previous page here. Okay, so I know the Laplace transform of t squared, but I actually want the Laplace transform of t squared multiplied by this exponential. So I can use the first translation theorem, which is this third entry here, this third translation theorem, to find this Laplace transform of this product here. So here the exponential of at, the a is equal to -1. Okay, so therefore the Laplace transform, 2 times the Laplace transform of t squared e to the minus t is equal to this thing, 2 times 2 factorial over s cubed, but wherever we see s, we're going to replace that with s minus a, or s minus minus 1, which is equal to s plus 1. So here we get 2 times 2 factorial over s cubed, but the s now becomes s plus 1 cubed by the first translation theorem. Okay, by this first translation theorem. Okay, I could have actually done that backwards. I could have calculated the Laplace transform of exponential of -t, so e to the minus t, calculate the Laplace transform of that, and then I could have used this property here, the second to last one here, to calculate the Laplace transform of t squared times the exponential function. So I could have used this other one down here as well. But just to summarize here, the Laplace transform of that, the original problem, well, we can write that like so. Let's look at another example here. So we're looking at the Laplace transform of t times the exponential of 2t times cosine of 5t. So there's a lot of things going on here. We're multiplying at some function cosine times an exponential times a polynomial. So we've got to take this step by step. So recall that the Laplace transform of cosine of 5t is equal to s over s squared plus 5 squared, so 25. Let's consider the Laplace transform of t times cosine of 5t. Okay, so the product of a polynomial times this cosine of 5t. So this property that I introduced down here is telling me, okay, well, let's first say it's t to the power of 1 So in this case, n is equal to 1. Okay, so we're going to get negative 1 to the power of 1, so negative 1, times the first derivative, so d over ds, of the Laplace transform of the original function. Okay, so we're going to get negative 1 times the derivative with respect to s of this fraction here. Okay, so Laplace transform of t times cosine of 5t is equal to negative 1 times the derivative with respect to s of this fraction. Okay, well, that's not too hard. We can calculate the derivative of this thing here. You can use the quotient rule, or you could even use the product rule if you so chose. But it turns out that this is equal to s squared minus 25 over s squared plus 25 all squared. Okay. So now we've used that property, that polynomial property, to find the Laplace transform of t times this cosine. But now we need to use the first translation theorem to find what this thing is, t times cosine 5t times e to the 2t. Okay, so first translation theorem with a equal to 2. So a equal to 2. So wherever we see the function f of s, wherever we see an s, we're going to replace that with s minus a, or s, in our case, s minus 2. Okay, so that becomes then, up here we have s squared minus 25, so we get s minus 2 squared minus 25. On the bottom we have s squared plus 25 all squared. So we get s minus 2 squared plus 25 all squared. So this first translation theorem and even the polynomial theorem, we're going to need to know this carrying on, know this for the rest of this unit. Okay, so maybe feel free to take a moment to consider that and try and understand that. Okay, so we've looked at the case where if we have a function f of t, we take its Laplace transform to find f of s, right? So we can go one way. But sometimes we need to go backwards, okay? So let's consider this second order initial value problem. So we've seen initial value problems like this. This is a non-homogeneous initial value problem. It's a constant coefficient, so we can solve this, in fact, using the methods from Unit 2. We're also given two initial conditions, very simple ones. When t equals 0, y is 0. When t equals 0, y prime is 1. Let's take the Laplace transform of both sides of this ODE, okay? So the Laplace transform is linear, so we know that we can take the Laplace transform of each of these terms individually. So we get the Laplace transform of the second derivative of y minus the Laplace transform of y is equal to the Laplace transform of minus t. Okay? Oops, going backwards there. Okay, so well, the Laplace transform of y is just going to be capital Y of s. The Laplace transform of minus t is just going to be negative 1 over s squared. The Laplace transform of y double prime, well, here we're going to use this property of Laplace transforms. So the Laplace transform of a second derivative is equal to s squared times the Laplace transform of y minus s times the first initial condition minus the second initial condition. So in fact what we get is s squared times the Laplace transform of y, which I'm writing as capital Y, minus s times the first initial condition minus the second initial condition. So that's the Laplace transform of y double prime, minus the Laplace transform of y, which I'm just writing as capital Y of s, equals negative 1 over s squared, which is the Laplace transform of negative t. Okay, but my initial conditions say that y of 0, so when t equals 0, y is equal to 0, my first initial condition. My second initial condition says that when t is equal to 0, y prime, the derivative of y, is equal to 1. So I can simplify this down like so. I can say s squared times y of s minus 1, that was that second initial condition, minus y of s is equal to minus 1 over s squared. Let's simplify that because we have we want to get y of s on its own. So I'm going to have s squared minus 1 amount of y of s on the left hand side. I can take this plus 1 to the other side, of course. So I end up, if I solve that algebraically, y of s is equal to negative 1 over s squared plus 1, all over s squared minus 1. And in fact, I can write that, what's on the numerator there, as, well, over a common factor, so over a common fraction here. So we get, we can cross multiply, we get s squared minus 1 over s squared times 1, or s squared. Okay, and this simplifies things quite a bit, because here we have an s squared minus 1 on the top here, divided by an s squared minus 1, so that is going to cancel out to be 1. And we're going to get left with 1 over s squared. So in fact, our y of s here is equal to 1 over s squared. Okay, so great. So we've solved this ODE, in fact we've solved this initial value problem in the new domain, the S domain, y of s. Okay, but we don't want the solution in the S domain. We want the solution in the original domain, which is the T domain. Well, maybe it means time, let's say. So in the time domain, the T domain, we want to find the solution lowercase y of t, not the capital Y of s. Okay, so we need to go the other way. We need to find a function y of t which gives 1 over s squared when we take its Laplace transform. So the Laplace transform of this thing y of t equals 1 over s squared. But we know what that is, right? Because we have this, we know that the Laplace transform of a polynomial is equal to the Laplace transform of t to the power of n is equal to n factorial over s of n plus 1. So if n equals 1 here, the Laplace transform of t is equal to 1 over s squared. Okay, so therefore, Laplace transform of t equals 1 over s squared. Therefore, the solution to our initial value problem is a really simple one. Y of t is just simply equal to t. Okay, you may like to try and solve this using the methods from Unit 2 to prove that, in fact, it's the same solution. The point is, though, using this Laplace transform method, we can solve initial value problems in basically using one step. Taking the Laplace transform of all the terms, solving for this y of s. So this is just an algebraic equation that we've solved here. And if we can find its inverse of y of s, then we can find the solution in the original t domain. Okay. So that relied on being able to find the inverse Laplace transform. Okay. So if f of s is the Laplace transform of some function f of t, then f of t is equal to the inverse Laplace transform of f of s. So we write that as this stylized L to the power of negative 1. So we say that's the inverse Laplace transform of this function f of s. Okay. Okay. So this stylized L to the power of negative 1 is called the inverse Laplace transform operator. And, well, let's just look at an example. If we have f of s is equal to 2 over s cubed, well, the inverse Laplace transform of 2 over s cubed, well, we can write that as the inverse Laplace transform of 2 factorial over s cubed, because 2 factorial is 2 times 1 equals 2. So this is the same. And then we can use this nice property we have for the Laplace transform of polynomials here with n equals 2. So if n equals 2, we get n factorial, so 2 factorial over s to the 2 plus 1, so s to the s cubed, which is what we've got here. So we know that the inverse Laplace transform of 2 over s cubed is equal to t squared. Or, for example, if we have the function f of s equals 3 over s squared plus 9, well, we can look at our Laplace transform table and say, well, this looks a little bit like this, right? We have some function, so we got 3 over s squared plus 3 squared, which is 9. 3 over s squared plus 3 squared, which is 9. So we know this is going to be a sine, right? So this is going to be equal to sine of 3 of t. So you can look at it sort of like differentiation and integration. They're kind of like the opposites of each other. So sometimes if I'm trying to integrate something, I say, well, what do I have to differentiate to get this thing? Okay. In the same way, you can say, when I'm trying to find the inverse Laplace transform, well, what do I have to take the Laplace transform of to get this thing? So if I take the Laplace transform of sine of 3 of t, I get 3 over s squared plus 9. Okay. So we're going to look at some more examples of this in the following classes, but I just wanted to say here that the inverse Laplace transform is linear. So in the same way that the Laplace transform is linear, the inverse Laplace transform is also linear. So if we take the inverse Laplace transform of some constant times the function f plus some constant times g, we can break that up into the constant times the inverse Laplace transform f plus the other constant times the inverse Laplace transform of g. So the nice thing is we can split this up. It's linear. It can make our life a lot easier just knowing that this transform is linear. So let's look at another example before we finish this class today. We want to find the inverse Laplace transform of f of s, which is equal to 3 over s minus 1 to the power of 4. We remember that, firstly remember that the Laplace transform of t to the n is n factorial over s to the power of n plus 1, but we can use the first translation theorem to make this even better, right? So e to the at times t to the n, using the first translation theorem, is n factorial over wherever we see s, we're going to replace it with s minus a. So s minus a to the power of n plus 1. So that's by the first translation theorem. If we take a is equal to 1 and n is equal to 3, so if n is equal to 3, we get 3 factorial, which is 3 times 2 times 1 is 6, and a is equal to 1. Well, the inverse Laplace transform of 6 over s minus 1 to the power of 4 is equal to e to the t times t cubed. This is almost exactly what we have, right? The only difference is this is a 6 and this is a 3. So because it's linear, I can multiply that by a half. So what I'm going to say is that the Laplace transform, the inverse Laplace transform of 3 over s minus 1 to the power of 4 is just half of this thing up here. So it's half of e to the t cubed by linearity of the inverse Laplace transform. Let's look at maybe one more example. We want to find the inverse Laplace transform of, well, this is something that is a polynomial divided by another polynomial. Okay. Well, I can rewrite that denominator. Just I want to try and bring this into two terms here. So s squared plus 2s plus 10, I can complete the square on that and say this is equal to s plus 1 squared plus 3 squared times s. Okay, so well, that's because we get 1. I shouldn't have an s here. Hang on. So I just got rid of that s that shouldn't have been there out here. So okay, so in fact what I am saying is my second order polynomial, my quadratic here, s squared plus 2s plus 10, I can complete the square on that like so, right? Because now if I expand this bracket, I get s squared plus s, so that's 2s, plus 1 times 1 is 1. So I get s squared plus 2s plus 1. I need to add this 3 squared, which is 9, to get that 10, right? So I'm just completing the square on the denominator, so I can rewrite this fraction like so. This original function here, s plus 1 over s squared plus 2s plus 10, I can rewrite it as s plus 1 over s plus 1 squared plus 3 squared. Okay, this looks like something I've seen before, right? If this was just an s here, and this was just an s here, instead of s plus 1, if this was just an s, and this was just an s, this would look a lot like the Laplace transform of the cosine, right? But in fact, if I use the first translation theorem with a equal to -1 here, then I would get s plus 1 over s plus 1 squared plus k squared. Well, k here is going to be equal to 3, right? So always remember when we're using the first translation theorem, this a here, we're basically, wherever we see s, we're replacing it with s minus a. Okay. So it turns out that the inverse Laplace transform of this function s plus 1 over s plus 1 squared plus 3 squared is just equal to e to the minus 1t times cosine of 3t. So really what finding these inverse Laplace transform sort of relies on is first thing, you knowing the table of Laplace transforms, so knowing the Laplace transform of standard functions like polynomials, sine and cosine and exponentials, but also knowing these things like the first translation theorem, and also what happens if we take the Laplace transform of a function times a polynomial. Okay, so there's a lot in that lecture, so you may like to go and practice some of the examples from the study guide, but I'll see you in the next class.